Assalamu alaikum warahmatullahi wabarakatuh. Our lesson today is now going to be on the third lesson in Organic Chemistry 1, that is Form 3 work. So the subtopic is going to be on alkynes, Y-N-E. So that's going to give us our fourth topic, and this will be the last lesson in Organic Chemistry 1, that is Form 3 work. So, from the previous lessons, we looked at alkenes and alkanes, whereby we said that alkanes were saturated and characterized by single bond between carbon-carbon atoms, and alkenes with E and E are hydrocarbons which are unsaturated with double bond between carbon-carbon atoms. Today, we are going to check on alkynes which are characterized by triple bond between carbon-carbon atoms. Therefore, due to the presence of the triple bond between alkynes, that makes them to be unsaturated. So we say that alkynes are unsaturated hydrocarbons. They are unsaturated hydrocarbons. They are unsaturated hydrocarbons characterized by the triple bond. So the functional unit in alkynes, in alkyne is C triple bond. C triple bond. So this forms the functional unit in alkynes, and they have a general molecular formula of CnH2n minus 2. So we are going to have here general molecular formulae of alkynes is CnH2n minus 2, where N represents the number of carbon atoms. N is representing the number of carbon atoms. Therefore, if we look at the naming in alkynes, let's have a look at naming in alkynes. Naming in alkynes. Just as we were naming alkanes and alkenes, naming of alkynes also depends on the number of carbon atoms that they are having. The first member of alkynes is ethane. That is the first member. We don't have methane, so ethane forms the first member of alkene. From the word eth, that tells us that it has 2 carbon atoms. If it has 3 carbon atoms, that is going to be propyne. 4 carbon atoms, butane. 5 carbon atoms, pentyne. So we say that the first member of alkynes, the first member of alkynes is ethane with C2H2. Hydrogen, 2 hydrogens. Carbons, 2 carbon atoms. 2 times 2 is 4 minus 2, giving us 2 hydrogens. So that is the first member. So we have butane. We have pentyne, not pentyne but propyne. Propyne is C3H4. 3 times 2 is 6. 6 minus 2 giving us 4. We have 4 carbon atoms, butane, which is going to be C4H6. So as we start from butane, we are also going to find that the position of the triple bond needs to be identified. So that's now going to result in isomerism in alkynes. So we check on isomerism in alkynes. Isomerism in alkynes. So alkynes, being unsaturated, just like alkenes, they undergo two types of isomerism. The first type of isomerism is positional isomerism, and they also undergo branching isomerism. So if we first start with the positional isomerism, this is the shifting of the position of the triple bond across the structure. So the first two members of alkynes do not show isomerism, that is ethane and propyne. So they will not show the isomerism, meaning isomerism begins in butane. That's where isomerism begins. So we say that alkynes being unsaturated has two types of isomerisms. Two types of isomerism. The first one is branching isomerism, and the second one is positional isomerism. So if we first start with the positional isomerism, let me start with position. That is hydrogen, 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 hydrogen. This is hydrogen, hydrogen, hydrogen. That is pent one ion. Now I need to form the substituent group for me to be able to form a methyl. So a methyl is CH3. I carry this one here to form the methyl. When I carry this one here to form a methyl, I am supposed to insert it in the carbon on the carbon atom which is at the middle. Therefore, I either place it here or here. But this carbon atom is already saturated with the bonding. Therefore, I cannot form a methyl on this carbon atom because I'm going to have 1, 2, 3, 4. If I add a methyl here, it's going to have 5 covalent bonding, and the maximum number of covalent bonding that a carbon atom can make is 4. Therefore, I only have an option of placing this methyl on this carbon atom. Therefore, I'm going to have 1 triple bond carbon, carbon. I put my methyl there, then carbon there. So I'm going to have this one as hydrogen. This is hydrogen, 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 and hydrogen. Again, during the naming, our first consideration should always be placed on the triple bonding. Therefore, the triple bonding is nearer from this end. So if we make it from this end, the methyl here is going to be found on carbon number 3, and it is now going to be named as 3 methyl but 1 ion. 3 methyl but 1 ion. 3 methyl but 1 ion. So but is from the parent name. The parent name is obtained from the chain that has got the highest number of carbon atoms. The highest number of carbon atoms. So this represents the two types of isomerisms that alkynes undergoes. First one we have said is the positional isomerism, where we shift the position of the triple bond across the structure. And the second one is the branching isomerism, whereby we form a substituent group, that is alkyl group. Like methyl, we form an ethyl, we form propyl, and so on. Now the next part is on preparation of ethane, lab preparation of ethane. So we check on lab preparation of ethane. under the lab preparation of ethine. Ethine is prepared in the lab by reacting calcium carbide with water. We react calcium carbide with water, and the reaction is highly exothermic, and a lot of heat is produced during that reaction. Therefore, inside the round-bottomed flask, we can put some sand or broken glasses that is going to be used to absorb excess heat that might cause the breakage of the flask. So we say it's prepared in the lab, is prepared by reacting calcium carbide with water. So we react calcium carbide with water. So the reaction, we said that this reaction is highly exothermic, and a lot of heat is produced. Therefore, inside the round-bottomed flask, inside the round-bottomed flask, sand is placed to absorb excess heat that may cause breakage of the flask. That may cause the breakage of the flask. So, the reaction of calcium carbide, we have here calcium carbide, that is solid. We are reacting it with water molecules. This gives us calcium hydroxide, that is OH into bracket 2 aqueous plus C2H2 gas. So that is the product that is going to be formed when that reaction takes place. We place here 2. We get calcium carbide. This is calcium carbide plus water, giving us calcium hydroxide plus ethine gas being formed. So, ethine gas being a non-polar substance, and it is insoluble in water, so this gas here is going to be collected by over-water method. Ethine is collected by over-water method. Now, some of the physical properties of ethine. One, it is a colorless gas. Ethine is a colorless gas, and it has a pleasant smell when pure. It has a pleasant smell when pure. It is insoluble in water. This gas doesn't dissolve in water. And if you look at the molecular mass of this gas, it's almost similar to that one of air. So the best method used in the collection of the gas, we collect it by over-water method. Now we can check under physical properties of alkynes in general. So we check on physical properties of alkynes. What are some of the physical properties of alkynes? Some of the physical properties of alkynes. One, we talk of melting and boiling points. So the first one is melting and boiling points. Alkynes, being molecular substances, generally they have low melting and boiling points. This is due to weak intermolecular forces of attraction. So the intermolecular forces of attraction existing between the molecules of alkynes is weak van der Waals forces. and this requires less energy to be broken. But how does the melting and boiling points compares when we talk of across the down the group, or as the molecular mass of alkynes increases? Just like alkenes and alkynes, the melting and boiling points of alkynes increases with increase in molecular mass. So as the molecular mass increases, the strength of the intermolecular forces of attraction between the molecules also increases. Therefore, if I compare the melting and boiling points of ethine and maybe pentyne, I will find that pentyne will have higher melting and boiling point than ethine. Reason being, pentyne has bigger molecular mass, resulting into strong intermolecular forces of attraction than ethine. So we say that they have low melting point and boiling point due to weak intermolecular forces of attraction. But melting and boiling points, melting point and boiling points increases as molecular mass increases. As molecular mass increases, this results into increase in the strength of intermolecular forces of attraction. Then the next one, we check on solubility. How is the solubility in alkynes? How is the solubility in alkynes? That is the next or the second physical properties in alkynes. So we check on the second one is solubility. Solubility of alkynes. Solubility of alkynes. So alkynes, being non-polar substance, they are insoluble in water, but they dissolve in organic solvents like chloromethane, methyl, benzene, which are also non-polar organic solvents. So we say that are insoluble in polar solvent. In polar solvent into bracket water, but soluble in non-polar. They are soluble in non-polar solvent into bracket organic solvents. So polar is said, water is said to be a polar solvent because it has both positive and negative charge. It is partially positively charged and partially negatively charged. Therefore, water is referred to as a polar solvent. Organic solvents are non-polar because they possess no charge. So you will find that those substances which are non-polar, like these ones here, they are soluble in non-polar solvents. Like chloromethane is an example of a non-polar solvent. We have methyl benzene, which is also a non-polar solvent. Therefore, they will dissolve in those. But how does the solubility compares in these polar solvents? You will find that their solubility is decreasing as the molecular mass increases. But solubility decreases as molecular mass increases. So their solubility is going to decrease with increase in molecular mass. It's decreasing with increase in molecular mass. Then the last physical property that we can talk about is density. Just as in the previous lessons, we said what determines the density of these substances is the molecular mass. So as the molecular mass increases, we also expect the density in alkynes to increase. So density increases with increase in molecular mass. Density increases with increase in molecular mass. Now the next part is on chemical properties. We check on chemical properties of alkynes. Chemical properties of alkynes. Chemical properties of alkynes. So looking at the chemical property we said refers to how alkynes react with other substances. That is what we refer to as the chemical properties. So the first chemical property that we are going to check into is combustion. Alkynes, being unsaturated, since they have triple bond between carbon-carbon atoms, so you will find that they are burning with a yellow sooty flame, unlike alkanes. Alkanes were burning with a blue flame, alkenes were burning with a yellow sooty flame, and alkynes also burns with a yellow sooty flame. Reason being, alkenes and alkynes are unsaturated. Alkenes having double bond and alkynes having triple covalent bonding. So the first chemical property is on combustion. So we say that alkynes burns in air. Alkynes burns in air with a yellow sooty flame forming water and carbon 4 oxide. So this is under complete combustion when we have excess oxygen. Under limited supply of oxygen, instead of obtaining carbon 4 oxide, we get carbon 2 oxide and carbon. Some black specks will also be observed. So the reason why here we not only get carbon 2 oxide alone but also carbon, because the degree of unsaturation in alkynes is much higher. Therefore, a lot of energy will be needed to break the strong triple covalent bonding. So we have carbon, that is C2H2 gas, that is ethane plus oxygen gas. This gives us CO2 gas plus H2O liquid. So here we have excess oxygen. When we have excess oxygen, we call this one complete combustion of ethane. Complete combustion. So we need to balance off this chemical equation. In the balancing of this chemical equation, we have here 2. We can put here 2. We have 2 carbon atoms. The hydrogens are balanced. 2 carbons are also balanced. What is not balancing is oxygen. This one here is 4 plus 1 is 5. Here we have 2. We can use 5 over 2. So if we use 5 over 2, I'm using a fraction in balancing. So I'm going to multiply everywhere by 2. I put here 2. This 2 now changes to 4. And this one becomes 2. So that equation is going to be balanced. We get carbon 4 oxide and water. Under limited supply of oxygen, that is C2H2 gas plus oxygen gas, this gives us CO gas plus carbon solid plus H2O liquid. So the observation made during this reaction is the black speck, that is due to formation of carbon. Here we have limited supply of oxygen. This is going to be limited supply of oxygen. We get carbon 2 oxide plus carbon plus water. This is known as incomplete combustion. Incomplete. That is incomplete combustion of ethane. We have 2 carbon atoms. Here, this side, we also have 2 carbon atoms. We have 2 hydrogens, 2 hydrogen, 2 oxygen, 2 oxygen. Therefore, that equation is balanced. So one represents complete combustion and another one represents incomplete combustion. Now the next chemical property is addition reaction of hydrogenation. Addition reaction of hydrogenation. Just like we looked at alkenes, which were unsaturated, you will also find that alkynes which are also unsaturated undergoes a similar reaction of addition reaction. They undergo addition reaction, and similar conditions will be needed when carrying out the process of hydrogenation. So the second chemical property is addition reaction. Addition reaction. Under addition reaction, the first one is hydrogenation. Hydrogenation. Hydrogenation is the addition of hydrogen molecule across the triple bond in alkynes. So the first step, we are going to get alkenes, then alkenes gets hydrogenated to alkanes. So we first get an alkene and finally obtain an alkane. So which means this reaction occurs in a step-by-step reaction. So we say that alkynes are first converted to alkenes, then alkanes. So the condition needed for the process of hydrogenation is nickel catalyst and a temperature of 180 to 250 degrees Celsius. So the condition for the reaction is 1, we have nickel stroke palladium. We talk of palladium catalyst. We can either use a nickel catalyst or a palladium catalyst. And the second condition is temperature, a temperature of 180 to 250 degrees Celsius. So that is the two conditions that are needed for the process of hydrogenation. So if we have ethane, which is the triple bond, that is hydrogen, hydrogen, plus the hydrogen gas, this gives us, we have here nickel catalyst, 180 degrees Celsius, we get C double bond, that is hydrogen, 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 hydrogen. This is ethene, while this one here is ethane, which means I've used 1 mole of hydrogen. So in terms of questions, you can be given the mole ratio of equation that is going to determine how that equation is going to take place and the product that's going to be formed when using the mole ratio of equation. So if I add more of the hydrogen, 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 plus another molecule of hydrogen, I'm now going to get hydrogen, 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 hydrogen. This is now ethane. So the final product must be an alkane. Here again, we have nickel catalyst stroke palladium and a temperature of 180 degrees. So if we just carry out the overall equation using 2 moles of hydrogen, then I'm going to have C, triple bond C, that is hydrogen, this is hydrogen, plus the 2 moles of hydrogen gas, resulting in the formation of C. This is hydrogen, 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 hydrogen. There I'm going to have a nickel catalyst and a temperature of 180 degrees Celsius. This is here is ethane. Here I'm obtaining ethene. Ethane, not ethene. We get ethane. So you can see, if I'm using the mole ratio of equation, I'm just going to get an alkane direct. So ethane giving us ethane turning to ethane under the process of hydrogenation. Then the next one is on halogenation. Halogenation is the addition of halogens. This is addition of halogens across the triple bonding in alkanes. In alkynes, this is addition of halogens. So we talk of halogenation. So this is now the B, halogenation. This is addition of halogens. And for example, if you add chlorine, which is pale green, you find that chlorine is decolorized. If I add bromine, bromine will be decolorized. So the color turns to colorless. So halogenation is addition of halogens. This is addition of halogens. Addition of halogens to the triple bonding. This reaction here does not need or doesn't require UV light or sunlight, unlike alkanes. And we looked one of the conditions which was needed under the process of when we were carrying out substitution reaction in alkanes with halogens. UV light was a condition that was needed to break the molecules into atoms. But in this one here, light energy is not necessary. But even if there is light energy, the reaction is still going to occur, but it will explode, meaning that the reaction is now going to occur at a faster rate. Again, if we use the mole ratio of equations, for example, if I have C triple bond, this is hydrogen, this one here is hydrogen, plus 1 mole of bromine, 1 mole of bromine, I'm going to beget, this one here opens up, I get C. This one is hydrogen, hydrogen, bromine, and bromine. So we call this one as 1,2-dibromoethene. 1,2-dibromoethene. Then we can still continue adding more bromine molecules on that. We are going to get C. We have here C double bond. This one here is hydrogen, hydrogen, bromine, and bromine. We are adding another bromine molecule. This gives us CC. So we have hydrogen and hydrogen. This is bromine, 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 and bromine. So we name this one as 1122 tetrabromoethane. So an alkyne has now changed to an alkane. That is due to the presence of single bond between carbon-carbon atoms turning to an alkane. So if I just write using the mole ratio of equation, I'm going to find that my equation is going to be C, I have here C triple bond. This one here is hydrogen and hydrogen plus bromine molecule. 2 moles of it, I'm going to get CC. So this one gives me hydrogen, hydrogen, bromine, 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 bromine. So I will get 1122 tetrabromoethane. So this reaction occurs in a step-by-step reaction. So first we get an alkene, then we get an alkane. So if the equation is in form of the mole ratio, you must check how many moles of the molecules are you adding across the double bond. Then you will know the name of the product that is going to be formed during the reaction. So I can either have this step-by-step reaction, or I just write this one here. And the last part of it is addition of hydrogen halides. Addition of hydrogen halides. So hydrogen halides are like hydrogen bromide, hydrogen fluoride, hydrogen chloride, and so on. So we are adding hydrogen halides across the triple bonding. So if, before I forget, you will find that this reaction is going to be the same when chlorine undergoes similar reaction with alkynes. If it is iodine, it is a similar reaction. If it is fluorine, it will be the similar reaction. But the difference is the colors of the halogens, but in all of them, they are going to be decolorized. Then we check on addition of hydrogen halides. Addition of hydrogen halides. In addition of hydrogen halides, so this is the addition of hydrogen fluoride, hydrogen chloride, and hydrogen bromide. Similar reaction is going to take place. So we are going to have here C. This is hydrogen and hydrogen. This is ethane. We are adding hydrogen iodide. So this bond is going to break up. We form double bond. So this is hydrogen, 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 and iodine. This one gives us iodine. We call this one as iodoethene. Iodoethene. If you continue adding more of hydrogen iodide, we have C, that is iodine, hydrogen. This is hydrogen, hydrogen. We are adding another hydrogen iodide. Therefore, we are going to get C. This one is hydrogen, hydrogen. This one is hydrogen, hydrogen, iodine, and iodine. So this is going to give us 1,2-diiodo. 1,2-diiodoethane. 1,2-diiodoethane. So that is the product that is going to be formed when that reaction is taking place. If I use chlorine, I will also obtain 1,2-dichloroethane. If I use bromine, I will obtain 1,2-dichloroethane, and fluorine 1,2-difluoroethane. Similar reaction is going to take place when I use other hydrogen halides. Now let's have a look at test for halogen of alkynes. Test for alkynes. Test for alkynes. How do we test alkynes? How can you be able to distinguish alkynes from alkenes or alkanes? To distinguish, test for alkenes and alkynes are similar. So one is use of bromine water, which is decolorized, So bromine water is going to be decolorized under this reaction. Then another similar test for alkynes is going to be another one is use of oxidizing agents. Oxidizing agents. When we are using the oxidizing agents, one of the oxidizing agent can be acidified potassium manganate 7 ions or acidified potassium chromate 6 ions. So A, the first one is KMNO4. That is acidified potassium manganate 7 ions. This one, the color is purple. So if you add few drops of acidified potassium manganate 7 in a solution containing alkenes or alkynes, you will find that the purple color is decolorized. So purple color is decolorized. It turns colorless. Purple color is decolorized. So that is the observation that will be made during the reaction. And part B is if we use potassium chromate 6 ions, O7, that is H positive. This one here, the color changes from orange to green. So changes from orange to green. It will change from orange to green. So the orange color is due to chromate 6 ions and the green color is due to chromium 3 ions. While here, the purple color is due to chromate 7 ions and the colorless
the colorless solution is going to due to presence of manganese 2 ion. So these are the two ways on how we can carry out the test for alkynes and alkenes. But now, how can we be able to distinguish between alkynes and alkenes? Because similar tests are used in both of them. To distinguish between alkynes and alkenes is the rate of reaction. Alkynes will decolorize bromine water more faster than when we use alkenes. And at the same time, alkynes will have an effect on oxidizing agents more faster than alkenes. So that is how we can be able to distinguish between the two. And now if we can have a look on the uses of alkynes. Uses of alkynes as the last part of the topic. One use of alkynes, alkynes are being used in manufacture of polymers, in making of polymers, a process known as polymerization, since they are unsaturated. Another use we have ethine, which is used in oxyacetylene flame, that is in welding. We use it in welding, and that marks the end of organic 1 chemistry. That's the end of our lesson in Form 3 work, organic chemistry. Thank you.